Hi everybody! So over the last few days we've learned some of the information that we're going to need to know about differential equations and slope fields. What we're going to do today are a few examples of some application questions that you can expect to see not only within our unit, but very similar questions to this on the actual AP test. So let's start with this. Consider the differential equation dy over dx equals negative xy squared all over 2. Let y equals f of x be the particular solution to this differential equation with the initial condition f of negative 1 equals 2. What you're going to find as we start doing more and more of these examples is that the statements at the beginning are often very similar. They're going to give you a differential equation. They're going to say let y equals f of x, and then they're going to say the initial condition either in this part or further on in this problem. Now the reason I wanted to show you this is that this let y equals f of x part tends to confuse students. They're not really sure why the directions say that or what that means. You'll notice in this differential equation we have dy over dx equals negative xy squared all over 2. This has a y in it, not an f of x. If it was f, we would write f prime instead of dy dx. This, however, the initial condition says f of negative 1 equals 2. What this statement means is that the equation who has a y in it that we're talking about here is the same equation whose initial value we're talking about here. It's just a way of covering your bases to make sure that you know that this differential equation and this initial value are talking about the same function, even though this statement uses f of x notation and this statement uses y equals notation. It's really just showing that these notations mean the same thing. So, part A, sketch a slope field. Now we know that this is very useful for visualizing our solutions, but we also know this can be very tedious. I would strongly suggest taking your time. It's a very easy place to make mistakes, and it's also a very easy place to get a few extra points if you take your time and do it right. So let's talk about part A. Let's start with all the places where x is negative 1. If x is negative 1, then my differential equation becomes negative 1 times y squared all over 2. Now, two negatives make a positive, so it's really just y squared over 2. So this entire column of the graph is going to have slopes that are equal to y squared over 2. So let's graph those. Here, the y value is 2. 2 squared is 4, divided by 2 is 2. So I'm going to make an uphill slope. Here, the y value is 1. 1 squared is 1, divided by 2 is a half. Here, I'm going to make a flatter uphill slope. Here, the y value is 0. 0 squared is 0, divided by 2 is 0. We're going to have a horizontal slope. Now let's look at what happens if x is 0. So if x is 0, we're going to have negative 0 times y squared all over 2. Which means we're going to have 0 divided by 2, which is 0. So in this column of the graph, because the x value is 0, we are guaranteed that all of these slopes are 0, which is a horizontal line. Next, we're going to look at column where the x's are 1. So we're going to have negative 1 y squared all over 2, which means we're going to have negative y squared over 2. So we're going to do y squared divided by 2 and make it negative. Now you'll notice that's the same as this column, just negative. So what we can do is just take all of these slopes and flip them over and make them negative. Just make them go the same opposite direction. It's the same slope, opposite direction. And then, well, let's look at what happens when x is 2. So when x is 2, we have negative 2 y squared over 2. The 2's cancel, so we just get negative y squared. So we're going to take the y value, we're going to square it, and we're going to make it negative. Here the y value is 2, squared is 4, make it negative, we get negative 4. Here the y value is 1, squared is 1, make it negative, we get negative 1. Here the y value is 0, squared is 0, we make it 0. And that is my slope field. Now it takes a minute, or more specifically 4 minutes, but it's good to go slow and make sure we don't make a silly mistake. Part B here says write an equation for the line that is tangent to the graph of f at x equals negative 1 and use it to approximate f of negative 1.2. When I see the words tangent line, it requires me to remember and review something I learned a long time ago. To write the equation of a tangent line, I need to know that I need a point and I need a slope. Now the ordered pair here would be the ordered pair where x is -1. And to figure out my slope, I can use my derivative equation, which I have in my original directions way back here up at the top, because this is the derivative, the slope of this guy that I'm talking about. Now the first thing is I need to figure out the y value that corresponds to the x value being -1. Here's where we need to make sure we remember and read what was in the instructions. In the instructions, it told me that the initial condition was -1, 2. In other words, my graph goes through -1, 2. Now I can take that x and that y and plug it into my slope function. So I would have -1 times the y would be 2 squared divided by 2. Two negatives make a positive. 2 squared is 4 over 2 is 2. So now I've got a point and a slope. My third step when I want the equation of a tangent line is to write the actual equation. So I would have y minus 2 equals 2 parentheses x plus 1 in point slope form. Now it asks me to approximate f of -1.2. In other words, when you change the x, when you plug in -1.2 for your x value, what happens? So if I want to figure out f of -1.2, I'm going to start by getting the y by itself and changing it to an f of x. So I would have f of x equals 2 times x plus 1 plus 2. You may remember we sometimes called that a linear approximation or a linearization. Here we're just using f of x instead of L. Now I'm going to substitute in the -1.2 for my x. Now -1.2 plus 1 is -0.2. 2 times -0.2 is -0.4. And 2 minus 0.4 is 1.6. Now it's time to make sure we answered all parts of the question. It said, write an equation for the line that is tangent to the graph. That was step 1. So I would put a box around this answer and make sure that that is clearly stated, that that is the tangent line. Then use it to approximate. That's the second part. That's why we would have a box around this part of the answer. Last but not least, describe the location, all the locations for which the slope is positive. Now, we've done this a couple times, but let's see if we can figure out what happens, what makes our slopes positive. If I say the slope is positive, that means take your derivative function and tell me what needs to be true in order to guarantee that this is greater than 0. In order to solve this, if I think about it as a problem that I can solve an inequality function, I would multiply both sides by 2. So I would have -x times y squared is greater than 0. In order to make sure that the product of two numbers is greater than 0, in other words, positive, I need to look at those two numbers very carefully. This is going to be greater than 0. The y squared part is going to be greater than 0 all the time. Or it could also be equal to 0 depending on the value of y. Now -x is only going to be greater than 0 when x is negative. If I divide by a negative when I'm solving an inequality, I need to remember to flip the inequality symbol. So I can say that I can guarantee my slopes are positive when x is less than 0. But there's a catch. The other times when I could get a non-positive answer are when y is 0, because when y is 0, I would get 0 as my answer. So I would also have to state that y cannot be 0 in order to guarantee my slopes are strictly positive, not negative and not 0. Let's look at another example of a differential equation question. So this is a follow-up to the questions we just did. Find the particular solution to the differential equation with this initial condition. When you see these words particular solution, it should remind you of the problems that we learned how to do a while back, where we actually used our differential equation and our initial value to calculate the specific value of c. So that's what we're going to do here. Our differential equation is dy over dx equals negative x times y squared all over 2. We're going to start by separating the variables. Now, I personally find it easier to separate these variables if I rewrite the dividing by 2 as a coefficient. What I'm going to do is two things at once. I'm going to divide by the y squared, and I'm also going to multiply by the dx. So I'm going to have 1 over y squared dy equals negative 1/2 x dx. Now I'm going to integrate on both sides and use an antiderivative to undo the integral. So I would rewrite 1 over y squared as as y to the negative 2 dy, just to make my life a little bit easier when I do the antiderivative. The antiderivative would be negative 1 times y to the negative 1. The antiderivative of negative 1/2 x would be negative 1/4 x squared plus c. Now I'm going to try to isolate y. Now, unlike when I did my antiderivative and my integral, I think it's easier to isolate y if I rewrite the problem like this. So what I'm going to do is two things at once. I'm going to multiply by y and divide by this, which means I get negative 1 over negative 1/4 x squared plus c equals y. Now what I'm going to do is use my initial value to figure out c. So I'm going to plug in x and y. I'm going to have negative 1 over negative 1/4 times negative 1 squared plus c equals 2. Now I'm going to solve. So I'm going to have negative 1 over negative 1 squared is positive 1 times negative 1/4 is negative 1/4 plus c equals 2. Now I'm going to multiply by this on both sides. So negative 1 equals 2 times negative 1/4 plus c. I'm going to divide by 2, so I'm going to have negative 1/2 equals negative 1/4 plus c, because that makes this 2 cancel. And I'm going to add 1/4 on both sides. So c equals negative 1/4, because negative 1/2 plus a fourth is negative 1/4. Last but not least, I'm going to take this. I'm going to substitute it back into here. I should probably draw some arrows so I make sure I know where everything went. Substitute it back into there and write my final equation, which is y equals negative 1 over negative 1/4 x squared minus 1/4. If I want to make that look a little bit prettier, I can multiply everything by 4 on the top and the bottom, and I would get negative 4 over negative 1x squared minus 1. And that's my answer. So that's what it means by find the particular solution. Last but not least, this is another question that could be asked on our test or on an AP test if you had a differential equation. So find the second derivative in terms of x and y. Well, if we're starting with the first derivative, which I'm going to copy down, and again I'm going to rewrite it in a way that I just think is easier to work with. To find the second derivative, I would have to use implicit differentiation, because my function has a y in it. So let's review how that works a little bit. I'm going to treat the negative 1/2 like it's part of the x times the y squared as a separate thing. So I would use product rule. I would do first times the derivative of the second, which would be 2y dy dx, plus second times the derivative of the first, which would be negative 1/2. And then I would simplify. So I would have d squared y over dx squared equals the negative 1/2 and the 2 cancel. So I would have negative x times y times dy over dx minus 1/2 times y. And then a lot of students tend to stop And here's why you can't stop. In the directions, it says in terms of x and y. But this answer has a dy dx in it, and I only want regular x's and regular y's. So what we're going to do is take this function, which was dy dx, and we're going to substitute it, which means we're going to have negative xy times negative 1/2 xy squared minus 1/2 y. Now if I simplify that, I get positive 1/2 x squared y cubed minus 1/2 y, and that would be my second derivative. All right, last but not least, let's look at another type of application question. So that's the first sort of style of question. It's asking you to do some pretty algebra-y stuff with a differential equation. This is the second style of question we sometimes encounter on our tests and also on the AP test. It's an application question that asks you to use a differential equation in context. So the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the bird is first weighed, its weight is 20 grams. If b of t is the weight of the bird in grams at time t days after it is first weighed, then db over dt equals 1/5 parentheses 100 minus b. Let y equal b of t be the solution to the differential equation above with the initial condition b of 0 equals 20. Okay, the first thing here is don't let yourself get overwhelmed by just reading the question. All you really need to do is recognize that this is a differential equation with two different variables, b and t. Even though this only has a b, there are two variables, it's just there is no t, except for in the notation. And then let's work from there. Part A, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? So gaining weight faster asks you about the rate at which the bird is gaining weight. And it tells me in the directions, this function tells us the rate at which the baby bird gains weight. So to figure out how fast it's gaining weight, we need to take these two different values and plug them in. So the rate dB over dt when b is 40, because b represents the weight of the bird, and this is telling me it weighs 40 grams. If I plug that in, I get 1/5 times 100 minus 40. 100 minus 40 is 60, divided by 5 is 12. And it tells me that I'm measuring weight in grams and t in days. So this would be 12 grams per day because it is the rate. Now the second evaluation I need to do is dB over dt evaluated at b equals 70, which would be 1/5 times 100 minus 70, which would be 30 divided by 5, which is 6 grams per day. Now that I've figured out those two different rates, I can figure out when it's gaining weight faster. The rate is faster at 40 grams than at 70 grams. Now, logically, does this make sense? Do you gain weight faster when you're a young baby or when you're an adult? Well, if you look at how fast kids or baby birds grow, they're going to gain weight much faster when they're young and they weigh less to begin with than they are when they're an adult. Theoretically, as an adult, you shouldn't be gaining a lot of weight every year. So it makes sense that the baby bird is going to gain weight faster when it is younger, when it only weighs 40 grams to begin with, than later on in its life. So we would say the bird, and the reason I'm writing this is it says explain your reasoning. The bird gains weight faster when it weighs 40 grams because, so now that we've answered the question, we need to tell why. When it says explain your reasoning, it always means mathematically, not by just explaining it with words. So we would say because dB over dt evaluated when b is 40 is bigger than dB over dt evaluated when b is 70. Okay, second question that goes along with this prompt. Find d squared b over dt squared in terms of b. So it's asking us to find the second derivative in a very similar way to what we did here, where we found the second derivative. Only instead of x's and y's, we have b's and t's. So to find the second derivative, I usually start by copying down the first derivative. And then I also know this is going to be easier to take the derivative of if I distribute that 1/5 and I get 20 minus 1/5 b. Now here's the tricky part. In this problem, b is like a y. This b is acting like a y. So just like when we took the derivative of something that had a y, we needed to attach a dy dx in the previous example, we're going to need to attach something here when we take the derivative of b. So let's take the derivative. D squared b over dt squared equals. Now the derivative of 20 is 0, minus 1/5, and the derivative of b would be db over dt. Because remember, b is acting like a y, only instead of y's and x's, we have b's and t's. So instead of dy dx, we write db dt. Then we need to simplify. You'll notice it says in terms of b, which means we don't want a db dt in our final answer. So we would write d squared b over dt squared equals negative 1/5 times, and instead of dB dt, I'm going to substitute this original equation that we had up here. 1/5 times 100 minus b. Now if I simplify that just a little bit, this is all really one big multiplication problem, so I would have negative 1 over 25 times 100 minus b. You could also distribute that to both of these, and you would have negative 4 plus 1 over 25 b. It doesn't really matter. Either way, you just have to get that second derivative down. Last thing, use separation of variables to find dB or to find b of t. With the particular solution. So just like when we read this example here where it said finding the particular solution with this initial value, we're going to be finding this particular solution with that initial value using the separation of variables technique. So here's how I know I need to separate the variables. Not only does the directions tell me to do that, but also there are two variables. So just like I would have to separate the variables if there was a y and an x, I'm going to have to separate the variables if there's a b and a t. So to do that, I'm going to divide by the 100 minus b, and I'm going to multiply by the dt. So I'm going to have 1 over 100 minus b db equals 1/5 dt. Then I'm going to do the antiderivative on both sides. Now, I usually find it helpful to rewrite this with a power. But I also remember that there was a special rule for when our power was -1. It told us we needed to use the natural log of the absolute value of our function as part of our antiderivative. However, I also noticed that there's a negative here by the b. So to undo multiplying by a negative, I need to divide by a negative. I'm basically undoing chain rule by doing that. Now the antiderivative of 1/5 would be 1/5 t plus c, because remember our variable is a t now, not an x. Before I substitute my initial condition, I'm going to go ahead and isolate my b. So I'm going to start by dividing by this negative. So I'm going to have the natural log of the absolute value of 100 minus b equals negative 1/5 t minus c. Now, I don't actually need to change that c to a minus since it stands for a random number, so I'm going to change it back to a plus just so I don't get messy somewhere. Now, I'm going to raise both sides to the e power because e's and natural logs are inverse functions. So I'm going to end up with just 100 minus b equals e to the negative 1/5 t plus c. I'm going to rewrite this as a product because I know that if my exponent has a plus sign, it was originally a product, and I'm going to convert this to c number 2 and move it to the beginning. So 100 minus b equals c number 2, e to the negative 1/5 t. Then I'm going to subtract 100. And divide by a negative. Now you'll note that I'm not putting a negative here, and the reason I'm not putting a negative here is this is an arbitrary constant. It doesn't matter. We don't ever have to change its sign. We don't ever have to add them. Like, we don't have to do anything. It's just a random number. Once I get to here, I'm going to use my initial value and actually solve for c. So if I plug in 20 equals c number 2 e to the 0 plus 100. If I subtract 100, I get negative 80 equals c number 2 because e to the 0 is just 1. So now I can substitute that back into here, and I would have b equals negative 80 e to the negative 1/5 t plus 100. And I'm done. All right, I know this is a long one. I apologize. I wanted to take my time and make sure you really understood everything. We will definitely be practicing some more of these. Thank you so much for watching, and have a great night.